Hi everyone, welcome to the third video in Unit 3. This is increasing and decreasing functions and the first derivative test. And you can see here the objectives that we're going to be doing. We're going to be working on curve sketching. That's a topic in calculus that we're going to use calculus to sketch curves based on their first and then second derivative. So we've been talking in class about inflection points and increasing and decreasing in notation. We're continuing to use that in this video. So stay tuned. Okay, so for this first diagram, we can see here that we have, it's a piecewise function, right? We have it from here in this interval. It is decreasing. This is constant, and then the function is increasing. And I wanted you to look at what the notation is for each one of these. This is the most important thing. Here, once again, x equals a, x equals b. In this interval, the derivative, right, is less than 0. So the derivative, the slope of the tangent lines for this decreasing function is negative. The slope of the tangent line for each one of these points in this interval is going to be 0. And the slopes of all the tangent lines on an increasing function is going to be positive. And so that's what this test for increasing and decreasing functions. It just says let f be a function that is continuous on the closed interval and differentiable on an open interval, same as the others. If f prime is greater than 0 for all x in that interval, then it's increasing on that interval. If f prime is less than 0 for all x in that open interval, then f is decreasing. And if f prime is equal to x, then f is constant. F prime of x is equal to 0 for all x in the open interval, then f is constant. Now, what happens if it doesn't change from increasing to decreasing? Well, we would call that being strictly monotonic. Monotonic would be a function that is increasing over its entire domain or decreasing over its entire domain. So it does not change from increasing to decreasing. So in order to use the first derivative test and to determine the intervals of increasing and decreasing, here are 4 guidelines. All right, so the first one is you're going to locate the critical numbers of f and ab. We've been practicing that over and over. Find the derivative, set it equal to 0, find the critical numbers. Remember also that a critical number could also be where the derivative does not exist. So not only do we find it by finding where the slope is equal to 0, but we also look to see where the slope doesn't exist at all. We're going to make test intervals. We're going to determine the sign, positive or negative, of f prime of x at least one test interval in each of the interval, or each one test value in each of the intervals. And then we'll determine the intervals of increasing and decreasing. Okay, so here's the first example. We have f of x equals x squared minus 6x plus 8. All right, so the first thing we want to do is we want to find the derivative. So I'm going to find the derivative of f is 2x minus 6. I'm going to set the derivative equal to 0 to find any critical values. So I have 2x equals 6 and x equals 3. Okay, so now what I want to do is make what we call a sign chart. Now, sign charts are not, an acceptable way to explain why a function might be increasing or decreasing on an AP exam. They don't use that. You'll actually have to have a verbal component, but we're going to learn how to do that. But so far, let's just work it with a sign chart. All right, so we're going to put our critical value here. All right, now we've divided this into 2 intervals. So we have the interval that is less than 3, and we have an interval that it's greater than 3. 3 is our critical value. Okay, so I'm going to pick an easy number that's a whole number. Usually you wouldn't pick a decimal, but I'm going to pick a number in this test interval. I'm going to pick 5. All right. And then on this side, probably the easiest number to pick on this side is either 1 or 0. Okay, and then we're looking, this is a sign chart. sign chart. So we are looking at the signs on either side in either interval. So I put a 0 back into the derivative, and so I put a 0 in here, so that would get -6, so that would be negative. And then if I put a 5 in there, 10 minus 6 is 4, and so that would be positive. So we can see that on one side of 3, one side of this critical value, the function is decreasing. It's negative. And then on the other side of 3, it is increasing. All right, so I know that it's decreasing from -infinity to 3. That's decreasing because it's negative. And then it's increasing from 3 to positive infinity because it's positive on that side. Now, when we get to the first derivative test, we're going to talk about what this means in terms of extrema. So here's our second example. I have y equals x to the third over 4 minus 3x. And I'm going to do the same thing. I'm going to find the sign chart. So I got to take the derivative. So I find the derivative, and this is going to be 3/4 x squared minus 3. I'm going to set that equal to 0. Add the 3. And then multiply both sides by 4/3. So that's going to be x squared equals 4. And so x is going to equal plus or minus 2. So this time I have 2 critical values. All right. And so I'm going to make another sign chart. Only this time I'm going to have 2 values, -2 and 2. Well, I still want to pick values in the intervals. So between -2 and 2, the easy one is 0. Greater than 2, I'm just going to pick a 3. And then how about -3? Lower. Okay, so I'm just looking at the signs. I'm plugging it back into the derivative. So I put a -3 in to the derivative, and I get 9 times something, 27 over 4 minus 3. So that's definitely positive. Then if I put a 0 in, I get a -3. And if I put a 3 in, I'm also going to get another positive. And I'm estimating, right? I don't need the actual value. I just need to estimate. So if it's really obvious that it's greater than, then I pick that. Okay, so then I just write the intervals. So it's going to be increasing from -infinity to -2. Now remember, we're writing it on these numbers, not the interval, the numbers that we picked to test. And then it's also increasing from 2 to infinity. And then it is decreasing from -2 to 2. All right, so once again, we're using that interval notation to write our intervals, and that's what we're trying to do for that. Okay, these are big letters. First derivative test. First derivative test. So what we're doing here is we're supposing that c is a critical number of a continuous function. So say right here, right, this is c. c is a critical number of a continuous function. If f prime changes from positive to negative, then it's a local maximum, right? So if it goes from increasing to decreasing, plus to minus, then this is a max. And if it goes from decreasing to increasing, then it is a min. If it does not change signs, so for instance, it's increasing to here and then increasing here, then this is called monotonic, and there is no minimum or maximum, no extrema there. Now, if you're looking at this one, this point right in here would be the inflection, changing from concave down to concave up. So if we go back to our first 2 examples, and I've recreated the sign charts here, they're kind of funny looking, but I've recreated them here, then we can once again apply the first derivative test. So we know that in this interval right here, from -infinity to 3, we know that it is decreasing. And I kind of drew it before, right? It's decreasing. But on the other side of our critical value, it is increasing. So because there is a change from decreasing to increasing, we have a relative min. It might be absolute, we're not sure, but for sure we know that it is a relative minimum. Okay? And so, and we would say that it passes the first derivative test because it changes from decreasing to increasing. We would not use just the sign chart. We would actually use our words. All right, so here, this is increasing to decreasing, right? And this is decreasing to increasing. So we have a max here, and we have a min here. So we have a relative max at x equals -2, and we have a relative min at x equals 2. And that's the first derivative test, and it actually is kind of intuitive. So I'm hoping that you'll see how easy this is. So one more example here. One more example. We're going to find the critical numbers, and then we're going to find the open intervals of increasing and decreasing, and then apply the first derivative test to identify extrema. All right, so let's take the derivative. So the derivative of this function is 3x squared minus 12x, right? And then set that equal to 0. So I have that equal to 0. We're going to factor out. Now I'm going to double check it before I go. Okay, so 3x squared minus 12x, that should be right. And then, so I have critical numbers then at x equals 0 and x equals 4. So those are my critical values. So I make a sign chart, right? And I have 0 and 4. And so I need to pick a value in each of the of these ones. So I'm going to put a -1 here, and I'm just picking a number. I'm just trying to pick an easy number because I don't want to do a whole lot of math. And remember, you want to plug these numbers, these test numbers, back into the derivative, not into the original function. Okay, so if we put a -1 back in, I get, I'm going to put it into this one. Whoops. Put it into this one. That might be a little easier. So I've got -3 and then a negative. So this is going to be a negative times a negative is a positive. And then if I put a 1 in here, I've got a +3 and times a negative, so that'll be a negative. And if I put the 5 in there, that's a positive times a positive, which is also positive. All right, and this is hard to see, but what I was doing is I was doing 3 and then putting a number in for this, -4, right? And then looking at this sign times this sign. So if this is plus and this is minus, then that's going to be a negative. If they're both plus, it's a plus. If they're both negative, it's a negative, that kind of thing. And to me, that would be easier, but you could also put it into this one. It doesn't matter. It just needs to be in the derivative instead of the function. And if you're going to make a mistake, that's usually where you do it. In fact, I've done that before myself. All right, so we're looking here. This is increasing, and I like arrows. Doesn't this kind of point it out? So it's doing that. So I know that there's going to be a relative max at x equals 0. And then if you look here, this is changing, right, like that. So I know there's a relative min, relative min at x equals 4. All right, and we know that because it's the result of the first derivative test. When it changes from increasing to decreasing and from decreasing to increasing, that's when we know we have our extrema. If there was no change, then we knew there would be no extrema at that point. Now the last thing that I want to talk about on this video is Mrs. B's House of Calculus. This is a tool that I've run across and have used to help us put all of the pieces that we're going to use in this curve sketching unit together. It's called Mrs. B's House of Calculus. You can see that it has 3 different levels. I'm going to introduce it briefly, talk about it a bit and how the pieces fit together, but keep in mind this is an introduction, and we are going to be talking about this an awful lot as we continue to put the different tests. We learned first derivative test in this video, but there are additional things that we are going to learn about curve sketching. All right, so without further ado, let's talk about this. Okay, so you see there's 3 levels: the function, the derivative, and the second derivative. All right, and so we know that a function is either positive, so it's above the x-axis, or negative. If it's positive, it can also be increasing. The function can be decreasing. The function can be concave up, and the function can be concave down. And we learned from this video about the first derivative test. And what we learned was that when the function was increasing, the first derivative was positive. And when the function was decreasing, the first derivative is negative. Now what's interesting is that when the function is concave up, the derivative is going to be increasing. And when the original function is concave down, the derivative is going to be decreasing. And then also, the derivative can be concave up and concave down. Now here's another cool little thing. The second derivative. When the first derivative is increasing, the second derivative is positive. When the first derivative is decreasing, the second derivative is negative. When the first derivative is concave up, the second derivative is increasing. And when the first derivative is concave down, the second derivative is decreasing. And then sometimes the second derivative is concave up and concave down. So you can see the same pattern and kind of how they fit together. And so this one part right in here, you can see how they all fit together. If this is concave up, the second derivative is positive. If the function is concave down, the second derivative is negative. And so concave up, we know that the first derivative is increasing and decreasing. So there's a lot of information in here, and this is almost like a mnemonic that makes it easier to remember. So copy this down. We're going to talk about this a lot in class, and I will see you then.